This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
For Software Engineering Radio, this is Edaena Salinas. Today I have with me Charlie Berger. Charlie Berger is the Senior Director of Product Management for Oracle's Machine Learning and Advanced Analytics. Charlie has over 30 years of experience in data analysis and has worked at Oracle, Thinking Machines Corporation, Honeywell, among many others. He's responsible for the product management of Oracle's machine learning, data mining, predictive analytics, text mining, statistical functions, and works with Oracle customers and other Oracle applications development teams to design and deploy predictive analytics through the enterprise. Previously, he was the VP of Product Management and Marketing at Thinking Machines Corporation. Charlie is also a technical evangelist. He holds a Master of Science in Manufacturing Engineering and a Master of Business Administration from Boston University. He also holds a Bachelor of Science in Operations Research and Industrial Engineering from the University of Massachusetts at Amherst. Today, we will talk about machine learning and predictive applications. Charlie, welcome to Software Engineering Radio.
Thank you for having me.
Thank you. You work at Oracle in machine learning and advanced analytics and predictive applications. What is a predictive application?
Well, a predictive application is simply taking a predictive model that you've built that may have in the past been left on on a laptop or a single server or an open source package, and it's putting that into the enterprise, putting that into some sort of production or operationalizing that predictive model. That's where it's all. That's what it's all about. Is putting your insights and your predictions into some sort of real time operational kind of a situation. I'm always impressed that when I go to my bank and I go to the ATM machine and I swipe my card and stick it in the ATM machine, the very first question it asks is, "Hello, Charlie Berger. What language do you want to use?" As if that may have changed. And what I would expect today in 2017 is for it to have observed all my previous behaviors and transactions, and for it to come back with a suggestion or a recommendation that says, "Hello, Charlie Berger. Would you like to take out an extra $100 cash, like I've noticed you usually do on Friday nights?" Getting ready for the weekend. So that's what I really would call operationalizing a predictive model into a predictive application.
That's a good point. Learn from the previous data. And a lot of enterprises are using predictive applications more and more. Before these existed, what were companies doing? Was there no predictive analysis?
No, predictive analysis has been around, of course, for years. I think it goes all the way back, of course, to Bayes, way back in the 1700s with his, Bayes' theorem and conditional probabilities. And people have always been, looking at patterns and things, but oftentimes in the old days, I guess it would be in their heads. Later on, it might be some sort of statistical model using data sampling and building some sort of regression or some sort of model based on that. But over the last, say, 20 years or so, neural networks, decision trees, clustering, a bunch of different machine learning algorithms and tools and software and open source have all emerged. And it's really a fun and exciting time these days. There's so much going on. But many of the machine learning use cases were something like, I took a set of data, I analyzed it, I used this algorithm, I got a slightly better result and a better fit, or I used this algorithm and got an even better fit. So there were too many, I guess, published papers, too many people doing sort of laboratory experiments in their office or on their desktop, and never actually worrying about getting that into production. Now, the database marketing field, I think, was one of the earlier fields that did this just because that was their business. They would take data out of oftentimes a relational database, move it to something like a traditional software package, or perhaps more recently, perhaps open source, but they'd build the models in a separate analytical environment. And then they would somehow need to take those predictions and take the models and score them against the data that's, whereas that data, it's oftentimes in a in a data repository or database or something. And that was a very sort of outer loop process. And they do that very mechanical, very outer loop. And then they'd have a list of people, and then maybe they'd send you an email or make a phone call to you or something like that. But it wasn't that much more real-time operationalized kind of deployment of machine learning that you would more and more expect today.
Mm-hmm. Yes, what you're talking about now is we have people working in a laboratory doing the experiments, but the data is somewhere else. So they take the data to use it in the models. And we'll actually talk about this later on, and also about the other idea of moving the models to where the data is. But before we talk about that, I want to understand more about predictive applications. Like you said, before we would have the models, but the applications were really being built. Why do you think we are building them more now?
Well, it's because it's the art of the possible. It's what people can do these days. There's so much data and digital exhaust from people. It's the datafication of everything these days. So you have so much more fertile inputs to predict and do just about anything. And you see that all the time. Things like, I think it's called Farecaster, that will predict whether or not when you buy an airline ticket, is it likely the price to go up or down. And on your Droid, you're always getting recommended stories, and you're getting things all over the place. We're also at Oracle. We have a lot of enterprise customers and a lot of developers that want to build enterprise applications. That's been sort of our strong suite for some time. And like we've had these Oracle Code events that have a bunch of developers come in and say, well, I have this whole ecosystem of building things around the enterprise data and the enterprise applications. I want to enhance them and do more. So what they were able to do is just leave the data right where it is and build some sort of predictive application. But they're able to do it so much more easily. Well, can I tell about an example application? Would that help?
Yes, you can mention that example if you want.
Well, to me, it's a very good example. It kind of sets the stage for all of them. You could imagine an application. We actually have something called Oracle Human Capital Management. It's called Oracle Human Capital Management, and there's a module in there called Workforce Predictions. And so what that does, it's just sort of basic. It says, okay, I know each employee, I know their salary, I know where they stand compared to their peers, I know what their dental plans are, how many children they have, I know how long they've reported to the same manager, I know maybe the manager's reviews or the employee's reviews. I have lots and lots of variables and a lot of derived variables that I can use for inputs. And so what you can do, and what we've done, is just say, well, I'll take all that and I will build predictive models and predict the likelihood that any employee is likely to voluntarily leave the corporation. We also predict their performance, but we don't do it as a separate outer loop, or the data science has been long ago automated. So what you do as a manager, you go into your application, you just see your employees, and you see like high surf warnings, almost like, watch out, this guy or woman is maybe more likely to voluntarily leave us than somebody else. And then because it's a real predictive application, you don't want to just stop there, right? You don't want to say, Joe or Sue are really likely to leave. You want to say, well, why? And so you need to sort of interrogate the model and find out, in the simple sense, you'd say what the coefficients are, but it could be any variety of models. But you want to know the reasons why, and it may say bonus. Maybe the bonus was really high, or maybe it was really low. It was high enough that they could retire or quit or buy on island, or maybe it was too low, or maybe it was good, but maybe compared to their peers. You need to have this sort of just-in-time communication of what we mean by the model, sort of the explanation of why that prediction was made. And then you really would, if you take it further, you'd say, well, I'd really like to, before I give the person a bonus or change their title or have them forgive some sick days or whatever I want to do, I'd like to do what-if analysis. So what you can do is you can actually have a little slider bar, and you can say, well, what if I forgave? I have a discussion with the person. I found out they have a sick grandmother and they've been taking a lot of sick days for themselves. Maybe if I take my slider bar and say, what if I were to forgive the 25 sick days? Well, what would other level 4 Java programmers, typically do? And you get a prediction of that, and you can make a decision sort of there on the fly. So it's that type of interactive, predictive application that I think is just becoming the expectation these days.
Yeah. And in this example that you mentioned, the main consumers of it are managers, the HR department. For other types of predictive applications within the enterprise, what are other consumers that can exist?
Oh, I mean, it's across the board. There was a great book. I'm going to mention probably a couple of books along the way called Big Data by Victor Meyer Schoenberger and Kenneth Cooker. I'm just looking around my shelf over here. Great book, and in there they talk about how in New York City, the fire department had way too many buildings to try and inspect. So they got a bunch of data about each of the different buildings, and they built predictive models. And one of the factors were, did the person who was managing that building, they take out a permit to do maybe some brick repair on the outside, or to fix the plumbing, or to do different things. And those kind of pieces of data were predictive in nature of whether or not that building was being maintained well and was maybe not a crack house or a fire hazard or something like that. So if you have limited resources and you're driving around as a fireman or an inspector, and you need to do building inspections, you would put those houses that were well maintained as, through this prediction lower on the list, and you'd sort of prioritize your resources. And you see those kind of things, more and more these days. And I expect quite a bit more in the days to come.
Yeah. What do you think is making these applications more common? Is it the technology specs?
Yeah, I think it's what I think of it is the what they call the datafication of everything. Everything is been digitalized. You have data. You have higher performing computers. You have advances in machine learning. You put all these things together, and you have a very powerful soup that can do a lot of very innovative things. And you also have greater and greater expectations. I don't know about you, but when I go on vacation, and I read a fair amount of sci-fi kind of books, but when I go on vacation, I have no idea what book I'm going to read, but I just go to Amazon and I look at my past books that I've purchased. I look at recommendations, and I'll review the recommendations, and I'll buy that book. It's just sort of the expectation. So if I'm a salesperson, for example, I would expect that before I start dialing for dollars, calling people, that I would have a list presented to me, or an interactive application, or maybe on my mobile droid, it would say, go see Charlie and sell him this product because he really, really needs that product per my prediction. I think you'll see that, really across the board more and more.
Yes, exactly. One of my coworkers, actually, for his son's birthday, he got whatever Amazon recommended, and he said his son really liked it. So
yeah, I think the future is going to be a lot of fun because it just keeps on getting better,
yes.
and better. You'll have less and less of these, what do they call it, spoofing phone calls trying to sell you something, and you'll have if the phone does ring, you'll know it's a good thing.
And we've been talking about this datafication time. Where can the data come from for a predictive application? What are some examples?
Oh, geez. This is where you kind of run the gamut of, are we talking about what people are doing yesterday or today or in the sort of very near future?
What I mean are, what are some examples of data sources like logs or information from IoT, just in general, for predictive applications that are being built or have been built? What are the sources of that data?
Well, I think you have, it's all over the place. Facebook pics. If I have facial recognition, and you see me as a Boston person because I'm based in the Boston area, and you see me standing next to pictures of New York Yankees or New York Jets football teams, and you do facial recognition, you're gonna suspect that I've gone crazy or something, right? So that would be a source. Tweets, of course. If I change my address, any kind of there's a lot of data that I think people talk about, and people also highlight in demos. The demo is always somebody that's stuck on some daughter of an important person that's stuck stuck on a plane and does a tweet. And had we only known that, we could have saved the stock price of this airline. So those are all the demos. In reality, I think it's a lot more of the kind of data you can just get from data providers like Epsilon, Oracle as a data cloud. There's a lot of providers that will provide data to you. Last I looked at, I think Epsilon, I believe, had something like I know I'll probably get it wrong, but I think it was 850 variables on every man, woman, and child, if you will. So they know your age, your income. They know the average income in your zip code. They know the Blue Book value of car 1, 2, and 3. Some of the customers I've been dealing with know they know what my spend is in each major hotel chain on room, on restaurant, on alcohol, on parking, and so on. Knowing all that information, you can do some pretty good predictions.
You mentioned Epsilon. What's Epsilon?
Epsilon is a purveyor, I guess, of data. They also do a lot of analytics. So the way I think of Epsilon, and I know I'm probably going to sell them short a little bit, but Epsilon has, if you want to, let's say you and I wanted to start up a business selling yachts to different people, and we wanted to not target everyone who, not everyone's going to be able to afford a yacht or live near the ocean. So we might go to Epsilon and say, do you have any information about customers? Because we want to filter on just those people that make maybe more than $1 million a year, subscribe to Yachting Magazine, and live close 50 miles or closer to a large body of water. So that's the type of data they would have. There's other different data providers these days. I won't mention them all, but Epsilon is one that's very well known and popular. Oracle has their own Oracle data cloud, where we also have that type of data as well. It's from the old, I think it's Datalogix, I think was the original company. But in the case of Epsilon, which I know, I guess I'd say I have some, I have public reference customers that are using that. DX Marketing is a public reference customer that uses the Epsilon data set. And it's got, I think it's 850 fields, attributes is what we'd call them in the database, but variables about really everyone, every man, woman, and child, pretty much is the way I think of it. So they know your age, your income, they know the income and ethnicity of your zip code. They know what magazines you subscribe to. They know the Blue Book value. They know how many cars you have, and they know the Blue Book value of those cars. And if you think of all the myriad of variables you might ever possibly assemble on an individual, and try and take that all the way out to 850 fields of information, they have a lot of data. I was thinking also of if you ever want to see a really good use case of just having a lot of data and analyzing it well, look at some of the YouTube videos and what Cambridge Analytica did during the United States presidential election. There's some famous videos there about just the level of detail they had and how they used machine learning to target people who were more likely to vote one way or the other. Now that is a little bit more of what I'd call a one-off, right? It's every 4 years you may put that much effort into something. You may have a list, and you might send your people out to knock on doors or make phone calls. It still would need to be made much more into a sort of an application, a real-time application. Now, if you think of maybe putting that inside of a phone booth, or a voting booth or something, I bet that's probably illegal. But that's the type of idea of just deploying real-time predictions and insights whenever and wherever it's most appropriate.
And earlier in the show, we talked about the people that work in the labs and how they're disconnected from the data. And a lot of people build applications this way. It's a common way to architect it. Can you explain in a little more detail what this architecture looks like?
Well, what most people do when they build a predictive model, and we've all done it. The first thing you do is you go down to your DBA and whatever wherever they're storing the corporate data, and you say, can I have an extract of that data, and I need the following attributes on these records. And the DBA probably is busy, and maybe they get around to it, and they finally give you an extract. And the first thing you do is I don't want to say sneakernet it, but you move it over to some open source statistical programming or machine learning environment, or they use some traditional statistical or machine learning environment, and they build a model, and they may build a very good model. They may use XGBoost, they may use random forest, and they'll publish papers about how good that model is. But once they have that eureka moment, then they need to somehow apply that model to the rest of the data. And where's the data? Well, they oftentimes took a sample or an extract out of this larger data repository or data lake. And for them to apply that model, they have to move the logic of the model back into oftentimes a relational database. And for enterprise, Oracle focuses largely on sort of larger organizations and enterprises. And so oftentimes what people will do is they'll recode the logic of that model back into SQL. And the TDWI, Fern Halper at the Data Warehousing Institute, says that this is the industry average is 9 months. 9 months to operationalize a predictive model. I know guys at reputable banks, that data scientists that say, "Oh, I'm on the hook. I'm in trouble, Charlie. I'm on the hook. I got to do 2, maybe even 3 predictive models this year." And for where this technology is going, and certainly where Oracle has led the way, is to move the algorithms to the data. Data is big, and it keeps on getting bigger and bigger. Algorithms are small. So why don't we teach that data management platform how to do math? So if you do that, it really changes everything. And I have a friend. He was the VP of data science at a nearby bank here in the Boston area. And he reached out to me before I knew him, and he said, "Charlie, I use your product. It's the best thing out there for check fraud." And I asked him, is that because you're using our new anomaly detection algorithm that's good at detecting very, very rare events, like less than 1%, because we train on normal, and then we flag things that are sort of dissimilar to normal, kind of like Big Bird. And his point was, no, I have lots of examples of check fraud. So I use a standard classification. I think he was using a logistic regression, sort of the classic technique. But for him, the advantage was, and this is where I kind of part ways with some data scientists who think it's all about the algorithms. To me, it's all about the data and the derived data and what we sometimes call the engineered features. So for this particular data scientist, we eventually hired him. His notion was, I am going to look at a moving window of time. In the database, there's something called SQL windowing functions. Maybe other vendors have the same kind of concept, but it's taking a moving window of time, and like say the past 6 months, and it's going to say, what's the average number of checks that you've written? What's the average amount of those checks? What's the min? What's the max? And so now you have 5 or 10 variables that are this moving average of a window of time. And you also generate another variable that is the most recent 24 hours for those same, let's say, 6 variables. And then you derive another derived or engineered feature that is the difference between the longer term behavior and the more recent behavior, because that's what check fraudsters do. They set up an established credit, they have a normal account, and then they go berserk and start writing all sorts of checks before the banks can catch them. And those 18 variables in this sort of simple example are really nothing. You haven't even put it through a neural network or a logistic regression. It's those 18 variables that were cleverly derived, which is where all the domain expertise lies. And being able to then immediately operationalize that, because it's just a pipelined SQL query, if you will, or to do all that. That's how you sort of really operationalize, machine learning, I think.
And one thing that you mentioned is that a lot of it is not about the algorithms, it's about the data. And the difference in this other architecture that you talk about and that you worked on at Oracle is that the algorithms are moving to where the data is.
Yeah, they become part of the data management platform. When you install the data management platform, they come sort of, a library of machine learning algorithms are already embedded as part of that data management platform. Or on the cloud. Everything's on the cloud these days, of course.
What are the types of algorithms that can be moved to where the data is?
Well, all of our algorithms are moved. So I don't want to do like a feature list of Oracle's technologies, but we have about 30 algorithms inside the database, and about 30 that run on our Hadoop and Spark environment. And so there's decision trees, k-means clustering, logistic regression, generalized linear models, linear and Gaussian kernels, support vector machines, one class supported vector machines, market basket analysis. We do text mining, all those kind of things. I guess I'll briefly explain how we started on this journey. I don't want to give away any kind of secrets, but we did this, 15 or more years ago, so I don't think it's so much of a secret today.
Or at least to get an idea, like you mentioned, decision trees can be moved to the database, logistic regression. Just a brief example of decision tree can be moved to the data, and with that you can build an application that does X.
Yeah.
So just
let me explain how say a naive Bayes or an a priori market basket analysis algorithm work. They're both the a priori is the market basket, the old beer and diaper story. Although, by the way, that was not really the story there was way overtold and became urban myth over the years. But
for those that are not familiar with it, can you explain that diapers and beer story?
Sure, if they haven't already heard it many times before, but the beer and diaper story was actually came out of, it's told different ways. It's either told as Walmart or Osco drugs, and that they noticed some sort of correlation. They found a pattern of where I think it was on Friday nights, they would find a high correlation of beer being put in a basket and sold with diapers. And so the story then got even more enhanced. And so then this Osco or Walmart company then decided to move the beer and the diapers nearer to each other, right next to each other. So whoever's buying diapers also buys beer, who's ever buying beer also buys the diapers, heads on home for the weekend, and sales went way up because of that. If you Google that a little bit, there's some good sources on sort of demystifying the full story. They did find a correlation, but that was about it. But anyway, the associations rule that was used there basically just counts the number of items, let's say ketchup and hamburgers and hot dogs and buns or spaghetti and bottles of wine and so on, and it counts for each item that you have. What we do is we do frequent item sets. We just count pairs of things, and then we take the frequent item sets and do a little bit more conditional probability math on it. And next thing you know, we have an association rule. If I see ketchup and relish and hamburgers and hot dogs all in a basket together, then there's probably about an 80 or 90% probability that I would also see hot dog buns and hamburger buns. And that may represent 3% of all my sales going out of the door at the grocery store. But if I can bundle those things together, maybe I can sell more. Dunkin' Brands has been a public reference of ours that I can mention that have publicly talked about their use of market basket analysis to try and sell, more than just coffee goes with donuts, donuts go with coffee. But I think publicly they've talked about trying to elongate their day and sell sandwiches, PM flats, I think they called them, later on in the day. And so they wanted to know what would go well with that. A lot of other companies that I've worked with talk about making high profits off of selling drinks, sugary water. There's huge profits on that. So what things could I sell? Potato chips, salty soups, things like that would cause more takeout orders to include those drinks. But all that really is just using the database to count things. And so it's the easiest algorithm to implement natively inside the database. The naive Bayes is very similar. It just does conditional probabilities. Let's say I am selling motorcycles, and I count how many times people buy the motorcycles that they're 80 years or older, or 60 to 80, or 40 to 60, or 20 to 30. And I just bin the data, I count it, and I have the beginnings of a conditional probability model.
And what does it mean to have a native machine learning algorithm implementation in the database?
Well, we have them, just to be clear. Oracle has them both in the database, which is where we've been doing it sort of for the longest. We probably have our best, most mature versions of all that there. We also have them outside the database in the data lakes, in the Hadoop and the Spark world. And you can imagine, being able to export the models to other places and put them into real-time deployments and applications. But the algorithms in the database just means that it just opens all these doors for, if you're an application developer. As I said before, these Oracle Code events, we get a lot of interest in, like, well, I'm a DBA or I'm a developer, and I'm not necessarily a data scientist, but I'd like to build a predictive application so the ATM could recommend, take out an extra $100 cash. If I can learn the patterns in the database, then at the end we codify those patterns and relationships, those inputs, outputs of, say, a regression or a decision tree or whatever. They're at the end of the day a first-class object. They're secure, they're scalable. Everything when I run them is all fully parallelized because I'm taking advantage of all the machinery of what our enterprise relational database would do. So in the latest release that we've just come out with, if you have, I think the specs are something like over 600 million records and over nearly 400 variables or attributes, and you want to and 500 degrees of parallelism, you could build a decision tree or regression model in 1, 2, or 3, or 4 minutes. So that just sort of changes everything. Now that's the model build. If you have a model that takes you a long time to build, I would argue, let's say it takes a half an hour and you just don't have the patience, you can always just schedule it, right? It's like a long running query or something, or a report. But the beauty of that is by now having that predictive model be already built, maybe it took you 4 minutes and you did it, last night at midnight, whatever, and you did like 100 models. Now, every time you go to, let's say, an airline and you check in and you check in with the one suitcase and the one additional person that were part of your party, and then instead you show up with 12 other people and 25 extra suitcases, well, that may look like you're the coach of a sports team, and maybe they want to upgrade you or put you on another flight or do some sort of thing. So being able to do that in sort of real time is what it's all about. And if that model is just an actual SQL function, not a PL SQL procedure, but a SQL function, that can keep up with OLTP kind of demands.
And you mentioned you have a hybrid approach where some algorithms are native in the database, while other ones you can be using Hadoop and things like that. Are there some types of problems that are better solved when it's native versus when it's not?
I don't know if I'd quite think of it that way. I think of it more as where's your data and what makes the most sense. So I know a lot of people, there's sort of this pendulum swing all towards machine learning, then all towards Hadoop and Spark, and those are very, very important technologies and trends that we're all seeing. But I do think that sometimes people sort of skip right over the obvious, which is, well, what's the data they're going to use for that to solve that problem? Well, let's say I am ready to buy. I have another. I told you I'd reference a couple of books. Another book that I'm reading lately that I just love is this book called The Naked Future by Patrick Tucker. That says what happens in a world that anticipates your every move. And he outlines a lot of different sort of examples and scenarios that as soon as you hear them, you go, of course that's going to happen. So let's say I'm about to put in a quarter into my vending machine. It's not a quarter, let's say $1.25 to buy an ice cream sandwich. But somehow in the world of big data, I know the source of that ice cream sandwich. I know where it came from. And maybe it was manufactured in Los Angeles and I'm in Boston. Well, there might be in the big data world, there might be a bunch of sensors on the delivery trucks moving those ice cream sandwiches from Los Angeles to Boston. And along the way, it's saying, yes, it's 28 degrees. It's nice, chilly 28 degrees going through the desert in Arizona and so on. It's still 28 degrees. Oops, I hit a spike. It's up to 40 degrees. I don't really care that it was 28 degrees. That's not an important variable to me as long as it never trips anything. But I do care if it ever goes up to 40 degrees. And more importantly, I care, maybe did it ever go up to 40 degrees for more than a half an hour? Because if it did, then my ice cream sandwich, I probably don't want to buy that one. I want to go somewhere else. And so that data might be in a data lake. I don't need to analyze. I don't have to bring the algorithms to that data lake to do the analysis. I may just want to do a derived variable, or what we'd call an engineered feature, to say, did it come on truck 27? Because truck 27 had 14 incidents of it going above 40 degrees for more than a half an hour. And the driver of truck 27, and this data might be stored in the database, is Charlie Berger, and Charlie Berger has had so many accidents before, and the tires on the truck that Charlie Berger is driving are all bald, and on and on and on, right? I might not have certification. I might go over a lot of bumpy roads for my GPS tracking. So you really have to kind of think about what problem am I trying to solve? In this case, it's should I buy that ice cream sandwich in the vending machine? And what's the data that supports that decision?
In show 286, Intro to Machine Learning, a big discussion that we had was around data cleaning and the importance of this in machine learning, because a big part of machine learning involves grabbing features from different tables, shaping the data, cleaning the data, filling in empty values if you want. So I'm wondering, how does this work out with when the algorithm is implemented natively in the database? Does the database change and get cleaned also, or is it a copy?
Well, is it a change or a good place? The source data is always the source data, right? Let's say I have customer data about address, name, that kind of stuff. I have customer demographics about their education, their profession, their income, things like that. And then I have transactional sales transactions, things they purchase. So now I have like a 360, maybe I have customer service comments as well. So I have some unstructured data as well. And I join all those guys together. Well, I'm going to join them in the database just the way I would join them in any other environment. One of the advantages of bringing the algorithms to the data that I always think is a really differentiator for taking that approach is the data does not have to be flattened out into a well-behaved two-dimensional table, right? When it comes down to like what drugs, what transactions do you have, what purchases, that is just a vector, right? It's a vector, and I can tabulate the total number of purchases of beer or mustard or ketchup or wine or whatever, and I can bring those in as aggregates. And in fact, I can even compare the aggregates to others in the population, as I said before. But let's say we bring all that data together. We've done a lot over the years that I would argue some people have, maybe some people don't. But if we have missing values, for example, that struggle has been around for years. And what many people do and what we do is we replace the missing value with the median or the mode. Now that's default behavior. We just do that. It's called auto data preparation. When you have something like age and your target field is, let's say, motorcycle, yes or no, we tessellate or the space or carve up the distribution of age intelligently. We have three different ways of doing that. We can bin the age. Let's say it goes from -5 to 127. Let's say it goes to 227 because I have bad data in there. So what we're going to do is we're going to tessellate that either into 10 equal width bins, starting at with -5 all the way up to 227, or I'm going to do equal count. So I notice there's a lot more people in the 20 to 30, 30 to 40, and there's very few people in the 227. So I'm going to collapse that back down, and I'll have equal width bins. Or the most intelligent thing that we do, I think I call it genius beating. The developers that wrote it don't like that, but it really cuts the space with respect to the target field. So wherever you have think of it growing a decision tree and finding the cut points along just that one variable with respect to the target field. And then once we find those cut points, well, you can count. And as we said before, if I'm simply counting and I know what bins I'm in bin 1, 2, 3, 4, 5, and I have 512 degrees of parallelism, wow, I can do that lightning fast. So all of the data preparation is what we would call automatic data preparation. In fact, not to go on a rant here, but for the example in unstructured data, data management platforms over the years have gotten very good, very mature. So in the Oracle environment, there's something called Oracle Text that simply just tokenizes the data. So I have a bunch of emails or paragraphs or PowerPoints or whatever. It's going to give me a bag of words, word count, using a standard statistical kind of technique. And it's going to do that in any language. I think we support like 16 or I think it's 32 languages actually. There could be a thesaurus for that, and I can have a single or multiple language. And what it's going to do when it gets to say Charlie Berger and my customer support comments, it's going to say Charlie Berger called up, his cable box was coming out with a digital pixelation way too many times, and the word pixelation might appear 17 times in my record over the last 3 weeks. Well, 17 times of the word pixelation and angry and frustrated are going to be compared to the larger population using TF-IDF, term frequency and verse document frequency. And now we're going to have Charlie Berger, my age, my income, what the cable box generation is that I have, and all these unstructured comments that have now been essentially structurized into a vector of coefficients for how often I use those words versus everyone else. And I can do all that just as fast as lightning inside the data management platform, because as I probably have said a couple of times, we moved the algorithms to the data management platform rather than the other way around, because we inherit all these other capabilities. So when you talk about predictive applications, which is the purpose of the talk, I believe, and you say, well, now I can more easily do that, but also I've got issues of like security, encryption. Maybe some of those emails or comments that I have are my resume or my health and medical records, and I don't want to export all of that out to some separate open source or proprietary separate analytical server that has maybe a lot less security capabilities than a very powerful industry leader sort of data management platform has. So all the algorithms, all the math, everything are all sort of contained within that same platform.
Yeah. And what working on the database gets you is, like you mentioned, this automatic data cleaning, filling in missing values and things like that. But when I was first starting to get into machine learning, and if you look at most of the online courses and resources like Kaggle, where you can find a lot of data sets, they're all in CSVs or TXT files. Why do you think that is?
Well, because you're just starting out. I mean, some of those data sets are very famous, simple. Well, the TXT, it's the lowest common denominator, right? So like the Allstate insurance data set, in order for me to use that at, say, any major database player or open source, R, Python, Microsoft, IBM, Teradata, whoever, it's easy for me to take a 10,000 record sample and send it around and share it. There's also some data sets that over the years have just been very, very good. There's a CARS data set that every statistical company uses. I go back so far that I know the person who generated that original data set, Ernesto Ramos. But some of those data sets are just damn good data sets, right? They're really good for showing correlations between this and that. The IRIS data set everyone uses is just a CSV file. And then when you get into like the Enron text mining data set, then maybe that's a more complicated JSON representation. Some platforms we can ingest JSON data, others can't. But unfortunately, that's why I say there's just, in my opinion, a little bit too much emphasis on. I mean, there's a lot of people that need to learn machine learning, and I want everyone to learn it and feel good with it, just in the same way that people can all use Excel these days, right? It's just, do you know how to use Excel? Well, of course you do, right? So do you know how to use machine learning techniques? Of course you should, right? But to learn, you need small data sets, but to do real enterprise production applications of it, you need to take a lot more computer science, developers, DBAs, all that kind of stuff come into play a lot more than.
So an enterprise wouldn't really be converting their database to CSV or TXT for doing a predictive application. Okay.
If they're doing that just seems silly. Yeah, that you should not. I'll tell you my favorite developer. I guess I can't mention him by name, but he's a DBA at a company that was doing real time. I don't want to mention their name exactly, but it's a financial services. They approve. They're public. If you Google my website and stuff, you'll see it. Financial services. They do predictions about whether or not this money transaction of say $10,000 should be valid or not. And they used to take the data out, bring it over to, I'll call it a traditional statistical package, and they would build models, and it would take them 3 months to build the models, but more importantly, to deploy the models and put them into production, because the model, as we said before, was out there, and they had to sort of operationalize that and implement it as SQL queries and logic, if this, if that, if they're in bin 27 for age and this and this. Now the DBA would be the person that would assemble all that data, do all the transformations, do all the joining this table or this table or this table together, and finally put together all the data and then send it over to the two people that I know that were PhD data scientists, and they would use other traditional packages, or they convert it over to use our stuff, and they build very, very good models because they're brilliant people. But the DBA finally said, "Hey, wait a minute, you're taking all my hard work, putting all this data together, and all you do at the very end is press go on a machine learning algorithm," because essentially that's what machine learning is all about. and you're just using a neural network or decision tree or any kind of classification technique, geez, I can do that myself. So this DBA, and everyone was pretty happy with it, was building models that were about 95% the same accuracy as the other PhD data scientists, but building them, as an application developer, a DBA, in the same amount of time or less. So that, to me, that's what it's all about. It's transforming and extending your sort of I'll say previously not the smartest database in the world. If you're just storing your data there, it's a sort of a file cabinet, and now that database has become more of a thinking machine type of thing. Well, you should have all your applications should have not only historical points of view, but they should have sort of a prediction on every variable you have. What's my income actual? What's my predicted income? What's my checking account balance? What's my predicted checking account balance? And on and on and on. There should be a prediction for essentially every variable you have. If you manage to store it, there's actual, there's prediction.
Let's talk a little more about native algorithms in the Oracle database. When I was researching for this, I saw that you mentioned that it's done by mapping R to SQL. So I'm wondering, what does the R programming language provide you with?
I'd clarify or correct a little bit what you said. We map R to SQL, but R is a language unto itself that maps. Turns out base R maps 100% to base SQL. Right? I can take aggregates, I can take select, I can say things of that sort, and there are equivalent basic SQL functions. So all the small verbs of R map one-to-one to small verbs in SQL. So we do that. We call it the R to SQL transparency layer. But remember, I said we've already built in the proprietary algorithms, and we're up to about 30 generalized linear models, support vector machines, neural networks, random forest, PCA, SVD, all these kind of things. Those are all grown from the inside out of the database in the way I described earlier in the interview. They're proprietary in-database, highly parallelized, scalable implementations of workhorse algorithms that are traditional and cutting edge. And so now along comes R, and a lot of people that know R. Well, you can use your base R language to select the data, query it, maybe visualize it. But when you do something like, say, a box plot calculates the median in the first, second, third, and fourth moments of the data. If I have 1 billion records, I don't want to pull all that data out over to single-threaded open source R to do that. So what we do is we see what you're trying to do, and we push it down. So the calculations for the min-max standard deviation and all that are in database SQL implementations of that. So if you have 1 billion records and 500 degrees of parallelism on your enterprise database environment, or because you're a bank or a telco or a hospital or something, that R it'll be unbeknownst to you. To me, it's a little bit like Google Translate, right? I type something in one language and it immediately translates it to the other for high performance execution in the database. Now, if you come in with your script that you've already written and it includes RPart, a popular R package for doing decision trees, I'm going to stop you at the border and kind of say, hey, wait a minute, don't come in here with your RPart. You can if you want to, but I'm not going to add any value to what you're doing. You're just going to take the data, maybe do some aggregations, maybe some data prep, whatever you want to do in the database. And then when it comes to using RPart, you're going to do something called embedded R, where we do a call out through inter-process communication. We're going to take that data set, we're going to do a call out to your RPart package. We're going to build the model in a single threaded, memory constrained. Maybe you have a lot of memory and it's a big box, but you're still using open source R to do that. And I'm going to say, you can do that if you want to, but you're paying a cost. Did you know that we have an in-database implementation of decision trees called the Oracle Data Mining Decision Tree that can actually handle structured data, unstructured data, transactional data, all these kind of things. So before you want to port exactly your R scripts, I'd say stop, see if there's an equivalent high-performance parallelized in-database implementation of those algorithms, and use that instead. You'll be a lot happier. And if there is still something you want to do in R, you can do whatever you want, but let's say there's a XGBoost or something is the example I use that's an R package, and we don't have that yet, and you find it really important for some reason. You can do that with the callouts that I described before, but I would say you're using R in that situation a little bit more as sort of analytical duct tape.
Yeah, and you mentioned base R. Is that a different flavor of R, or what is base R?
It's just R without all the packages, right?
Okay.
You get ggplot, you get all the different packages that you RPart, whatever QC package, all the different packages you load.
I see.
9 or 10,000 packages in the R community, and I can download R, and it'll come in with essentially no packages. Then I go to CRAN and I download whatever packages I find are important to me, and people will download like dplyr. Well, in our latest release, we added support for dplyr, so you can use the dplyr commands and syntax. You will when you load up our Oracle Advanced Analytics, or in the cloud, it's already all installed for you, and in the on-premise it installs by default. But when you use our product and then you want to use open source R, you have to get open source R. But then you do sort of a post or additional installation. It's already done for you in an Oracle managed cloud or so. But we add about a dozen R packages, ORE stats, ORE data mining, ORE graphics, ORE this and that. In addition, like say ORE R Connect. So the R Connect that's in the open source community, the Oracle R connection, that's maintained and open sourced by Oracle. But then we have additional packages that map to our previously written proprietary, high performance, fully parallelized, scalable algorithms. You're going to be doing yourself a disservice if you don't, come and look at the database as a possible platform to do your analytics, but you want to keep going and use your R language and push down further, or use the drag and drop GUI, the Oracle Data Miner, or use which generates SQL code, and you can integrate R code as well. I didn't want to go into a whole product pitch here, but if you do go take a look at it, take a look at the whole spectrum of what we offer, not just the support for R, because that's probably the best I've seen out there, but there's a lot more to it.
Yeah.
But on the big data, on big data, we do the same thing. We use an R API, and we have our proprietary algorithms there as well. And we wrap MLlib and things like that.
Mm-hmm. And two approaches of machine learning are supervised and unsupervised. Which of these two can be implemented natively?
Everything. If I'm miscommunicating, everything that we've done is supervised, unsupervised. They're all implemented.
So for supervised, it involves labeling the data. I have, like the email example, we can flag it as spam, meaning we write that column. Are we altering the real data, the real tables with this supervised labels?
No, we're just going to, think of it as, if it helps, think of it as like any other package, SAS, SPSS, R, Python, whatever. You have the data, and then in our case, you don't move the data to another analytical platform. So if it's labeled data or unlabeled data, whatever, let's say one of the variables is this spam? Is this email spam? Or is this patient likely to have an unplanned? Let's say we go to, let's switch to make it more interesting. Let's go to a hospital or a healthcare kind of environment. They have a bunch of patients, and they've all come in for surgical procedures. And I need to know which ones I should be tracking because they might have an unplanned surgical readmission. And that costs me a lot if I have to do rework, if you will, and people die, and it's just not good. So you have a bunch of people in the past that have had to return to the OR to have some more surgery. So in that case, it's going to be labeled. Did they do a surgical? It might be even flagged like what was the date of their it might be two dates: date of original and the date of a follow-up. For example, we have, as I'm thinking of another feature, we have something called SQL patterns that detects like dropped calls on. I call you, you call me back, I call you back. Well, if I notice this, and this, I could flag that as a dropped call. So let's say we use some sort of logic to have a derived variable that says, yes, this in fact was a person who had unplanned surgical readmission, or this piece of email was spam. So that's just another field that's in the database, It's a label, but it's just another attribute in the database. So if I want to do supervised or unsupervised or whatever, it's just like any other. There's no difference that I'm misunderstanding the question.
Mm-hmm. Well, I was just wondering, like, if we are using the real database tables, because in the other approach, it involves taking a copy of the data, running the algorithms, but the real data is not touched. What I meant was, if we're working with the real tables and the real data, and some of machine learning involves adding additional data like these labels of something is spam or not. What I meant was if the real data was being modified, or if there's some temporary tables that we work with.
Well, you would do it. You would do it however it made sense. Let me give you another example. Let's say I have I'm trying to sell clothing, and I want to find people who buy a lot of shoes. And so I have shoe transactions, and I have customer, let's say at Macy's or I don't know all the different shoe stores, but I mean clothing stores, but Filene's, Macy's, one of these kind of places, and Lord & Taylor. And I have purchases of people, and I have their information, I have their credit cards, their transactions, but I also have all their transactions. I could do a tabulation of, in the category of shoes, tabulate for the last year what the total valuation was. That's just a SQL aggregate, right? Just a SQL query. And then I could have a derived variable that says, and if this is more than $500, create a new variable called big shoe spender, right? And so that would be a new derived variable that would be either added to the table, of customer table, or maybe it would be another table that said, my data mining labels. However you choose to do that, and your DBA is going to maybe have an opinion on that. But then when I go to build my model, I would just take the customers table and join it to the tagged data. Now, I usually don't see it done that way. Usually I just see it as another table added to the customer table, like high value spender, a big shoe spender, yes. Or maybe the dollar amount of them, or however I want to do that. It's just pure SQL at that point. And then I build my models. Now, all I have to do, now that I have my predictions, I don't have to repeat all that data. I would just actually build the join, by the way, could be persisted as a table, or more likely just done as a view, right? It's just a view, and I can materialize that view or not. There's all sorts of standard things DBA guys would do to productionize or operationalize it. That's why I was saying in this Oracle code kind of event, we're sort of going to the next wave of getting developers to go beyond just the traditional and now add predictive. But they would maybe have a view and then build the model. They can probably want to persist the model. We do have things called predictive queries that build the models on the fly, apply the models on the fly, throw the models away, and just return the results. But you're probably going to say, I'd like to interrogate that model. You turned me down for my credit, or whatever you did. What logic did you use? When was that model created? So you probably want to store and save the models, but they're just stored as first-class objects in the database. And then when I make my predictions, I would say, select customers where the probability of them being a big shoe spender is greater than 65%. So now I have a model, I have all the data, I just push that data through the model as a SQL apply function, and in nanoseconds it scores maybe millions of records, and then I would probably just want to persist that. I mean, it's just a SQL query at that point. It's a results table. I probably want to save that because I want to probably graph that in some pie chart or bar chart or something like that, or put it on send the results out to my ATM or my salespeople. But I don't have to persist and copy all the rest of the data. I just have the prediction, like yes, or maybe a dollar amount, like $7,000 of shoes for Charlie. And if it's a classification, I have the probability of that. We also do something called prediction details, which will, regardless of the algorithm, would give you like the top N reasons why, like, because, he's purchased a whole lot of shoes in the past, or he likes high-end shoes. He only buys one pair, but they're $10,000 a pair each year, whatever it is. And that would only bring you one, would bring you what? The prediction, the probability, and maybe the rules table. And so you're really only having your original data. Maybe you create another attribute, which is the labels. You build the model, you save the model for reuse or whatever, and then you have those three additional attributes. So that's all that it really is. It's very light incremental load on your enterprise system.
And it actually makes a lot of sense, and it's very intuitive to the regular workflow for using SQL. I've used it since I was in school, and those are the things that I would do. I would write a query like what you just mentioned, but it would be mostly like I would have a table of people and a table of hobbies and just a query that maps the person with the hobbies. But now with machine learning, I can even add more powerful insights, like using the probability that they would like to watch a movie as a new hobby and things like that, which come from those native implementations of algorithms, if I understand correctly.
Yeah, that's exactly it, and yeah, it's kind of exciting for you to make that comment, because my experience has been that I don't like the term data scientist. Everyone is calling themselves a data scientist today. Today, to be a scientist, you're supposed to have a terminal degree with a PhD, and a lot of people call themselves data scientists. They don't really, have that. There's no, control over who calls themselves a data scientist or not. But also, there's this sort of culture that the first thing I do is, go get the data from wherever the data source is, from the data lake or the database or wherever, and then take it over to my analytical sandbox and do my analytical magic on it. And it stops there. I mean, the example I often write about now with enough caffeine on board, remember, is the Netflix example, right? Netflix offered $1 million to the data scientist team that could come up with a better prediction. So they had to do 1% better. Nobody came in 1% better. I think they came in 0.85% better, if I remember it correctly. And they gave them $1 million regardless. And so that made the press. Everyone talked about that. But what no one remembers, and this is one of my operational customers included the story in one of their presentations, they said what no one remembers is that predictive model, that better model, was never operationalized. It was never put into use. Why? It was just too much this outer loop overhead complexity that Netflix didn't think it was worth that. Now, if you go back to my DBA story at the financial credit risk transaction use case, that DBA is saying, hey, I do all my data wrangling, my data assembly, my reports, whatever. Machine learning, the good thing about machine learning, it's all automated. So I find it's a lot easier and a lot more exciting about where this technology is going to have developers and DBAs who work with the data, know it real well, for them to incrementally learn. They're all science and math majors, for them to, remember that logistic regression course you took, 10 or 5 years ago or 20 years ago? That same thing exists as another SQL function in the database. You too can do that today. And I find a lot more success with customers who are database, computer science literate people who incrementally add the data science than data scientists who try to incrementally add the whole complexities of an enterprise data management platform. They just can't get from there to here as easily as the developers can do.
Or to me, the big insight was, remember that logistic regression or the math you learned in high school? Well, that is machine learning.
Yes, exactly. It's had many names over the years, yeah. Exactly.
Well, Charlie, thank you for taking the time to come on the show. It's been great talking to you about predictive applications and machine learning.
Thank you very much. Thank you for having me.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.